Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 4, Chemical Foundations, Part 4. Here are our objectives for today's video. Pause here. You don't need to draw the picture unless you would like to. So when we refer to our lab equipment, we'll be discussing its precision and its accuracy, both of which are important, but they are different from one another. So precision refers to how close measurements are to one another, or you could think of it as how reproducible the data is. So if you look at the two pictures off to the left, you'll notice that they are both precise, meaning all of the measurements are close to one another. Whereas accuracy, that's how close you are to a true value. So the image on the left and the second and the third image in are both accurate because they are centered around the true value, but the one on the left is much more precise. So we both want accuracy and precision from any piece of lab equipment that we use, but they are fundamentally different things. And so if we need to make a measurement more accurate or more precise, then there are different ways to make that happen. So typically, inaccurate data almost always comes from a miscalibrated scale, whereas imprecise data usually just comes from the fact that you have used the wrong tool for whatever it is that you are measuring. Like if you tried to use just a 1 meter stick to measure somebody's height, that's not going to be precise enough. You're not going to be able to tell the difference between somebody who is 1 meter 60 centimeters, which is my height, and somebody who's a 1 meter 70 centimeters, which is or probably most of you and much taller than me. But if you use that device, it would say that we're the same, and we're not. As here, you don't need to draw the table. All right, so I'm just going to take a moment and answer it with you. Most students typically are able to get this one correct when I've assigned this in the past. So the most accurate is clearly going to be the student C because their data is closest to the true value. And then it says most precise. So just because student C is the most accurate does not necessarily mean that he or she will have the most precise data. So we actually have to take a look in it. So between the first, for student A, there's a 0.8 difference. Wait, no. 0.14, wow. 0.14 difference, 0.14 gram, 0.014 rather, gram difference for student A. For student B, we again have a pretty significant difference. And then student C has the smallest difference. So just because student C is the most accurate will not necessarily mean that they're most precise, but in this case, they are also the most precise. Pause here. So there are two types of errors that could occur in a lab. Errors are fundamentally different from a mistake. Once we call something an error in a chemistry lab, it means that it is something that really is not avoidable, whereas mistakes you could avoid. So random error, there's just natural fluctuations in a measurement, and that's typically going to cause lack of precision. So if you are weighing something that only weighs 10 grams, a tiny bit of wind in the lab could actually cause fluctuations in the mass. You're not going to see that for like a person, but for small quantities, you will see pretty significant fluctuation, even if you move around the room. There's not much you can do about that. There are actually some scales that have boxes around them to prevent that. We don't have those, but they do exist. And then systematic error, that describes a fundamental flaw in the way that a measurement is carried out. So that could be a miscalibrated scale. So if you are a normal sized person and then you just step onto a scale and it says 40 pounds and then you step back off and you step on it, it says 40 pounds again, that's a systematic error. Your scale is not calibrated. So it keeps just giving you the same result, but it's not accurate. Pause here. So now we're going to switch gears and talk a little bit about unit conversions. We're going to use a method that's called dimensional analysis. All that means is that we are canceling out units in order to get from one unit to another. So unit factors are just a fraction that relate to equal measurements. So 12 inches over 1 foot over 12 inches, both are unit factors. These are treated as constants, which means that they do not impact significant figures. And you can use as many of those as you need. So if I haven't already done so, I probably have. There is a sheet of unit factors that I've probably posted to Google Classroom and/or given you a physical copy of. You will have this with you for all tests, quizzes, midterm finals. Anytime you need it, you will have this with you. This is what I use to make answer keys. While for problem sets, you certainly could look these up. I highly suggest you use this such that you get used to using it. All right, let's take a look at example number 8. So we're going to use, I'm just going to stick to the unit factors that are on this sheet. So we have 63 inches, and I'm going to convert this to centimeters. So if you take a look at the sheet, you will see that 2.54 centimeters is equal to 1 inch. I need to cancel inches with inches, so I put the 2.54 centimeters on top and 1 inch on the bottom. Some of you might say, can I do this with cross multiplying? And while you will get the correct answer for this particular problem, it's not going to be translatable to future problems. So I am going to insist that you do all unit conversions in this method, showing your work, at least for the time being. You put this into your calculator, and then because 63 inches has 2 significant figures, I need my final answer to also have 2 significant figures. So I make this 160 centimeters. So that is a person who is about 5'3" is 160 centimeters. Pause here. So I'm going to stick to the unit factors that are on the sheet. For things like time, if you have some of them memorized, that's okay to use them. So I'm going to first convert this to minutes, and then to hours, and then to days, and then I think I did 365. I don't think I did the 0.14. Yeah, or 0.25 rather. And then I put this all in my calculator and I round to 2 significant figures. And so to round it to 2 significant figures, I make this 150 years. Out of my calculator, I got 145.8650431. So because my starting number has 2 sig figs, my final answer also must have 2 significant figures, no matter how many unit factors I use and no matter how precise those unit factors are. Right, that is all for tonight. Thank you so much for watching and have a great night.